2 minutes. We're just waiting for Trump. Welcome to this webinar on training and deploying your first machine learning model with Azure ML, brought to you by Wintellect. My name is Janaki Ram. I'm an author, instructor, a Microsoft MVP and regional director based out of Hyderabad, India. It's my pleasure to bring you this session on training, building, deploying, and managing machine learning models with Azure. A quick introduction to Wintellect. Wintellect has been in the business of consulting instructor-led training and on-demand training for a while. They are known for their expertise on Microsoft technologies and Microsoft stack. The authors and the instructors and the core team from Wintellect has been authoring very useful, very valuable books. Most of us grew up reading some of these books that laid the foundation for .NET, Azure, C#, Visual Basic, and now more of contemporary technologies, including the cloud, DevOps, and so on. There are about 30 books that came from Wintellect's team and the instructors associated with Wintellect. And specifically for those who are attending this webinar today, there is a 10% discount on the virtual MOC courses, as well as some of the certification related training courses. The email mentioned here, which is Martha Garan, you can drop a note to get more details about the special offers for the attendees of this webinar. So let's get started. Machine learning is one of the trending topics and the buzzword in the industry. Many software aspirants, many software developers are aspiring to become machine learning developers and data scientists and play with AI related technologies. So I'm going to walk you through some of the core building blocks of Azure ML, and in that process also introduce you to some of the concepts like the lifecycle of machine learning model, followed by how do we train and perform inference, and how do we take advantage of the cloud for highly distributed training and highly scalable deployment and inferencing. So let's get started. As I mentioned, machine learning has been one of the most sought after skills by software developers and aspiring data scientists. But before we really get to understanding and learning the nuts and bolts of machine learning, it's very important to understand the workflow involved in training ML models and using them for prediction. So machine learning is very different from traditional software development. It's more iterative than anything that we have seen in the past. So typically machine learning involves taking a lot of existing data sets, splitting them into training and testing, and applying some of the well-known, well-defined algorithms and align it with the data that we have captured historically, and then evaluate the performance of this model, which is trained based on the algorithm and the past data set. And once the evaluation meets certain criteria and it is satisfactory, then we move that into a frozen model, which is going to be used with production data for performing prediction, classification, clustering, and grouping. So that is the high level life cycle of a machine learning model. So basically, it is taking almost a century old mathematical algorithms and statistical formulae, applying it to a lot of data and see how they actually perform. And once we reach a certain point where the algorithm is now aligned, tuned, and parameterize it for the data set that we have fed, we freeze that snapshot of the training and we call that as the fully trained model, and we move it on to prediction. So prediction can happen either in the cloud, at the edge, or on mobile devices, on desktops. Basically, wherever there is a compute device, we can actually run prediction. But training typically happens at scale, and that is where we need cloud. The other way of looking at machine learning lifecycle is from the lens of DevOps, data scientist, software developer, and sysadmin. So there are multiple stages involved in training a machine learning model. When it comes to infrastructure, the DevOps team got to provision clusters, provision nodes, and provision the whole infrastructure responsible for running the data science environment. So they will bring up virtual machines, they will install a variety of drivers like the NVIDIA GPU drivers. Then they configure runtimes based on popular languages like Python and R, and then they install frameworks like TensorFlow, PyTorch, Caffe, Microsoft CNTK, Apache MXNet, and so on. And once the environment is ready and configured by DevOps, it is going to be used by developers and data scientists to train the model and to fine tune. And this is where the iterative process takes place, where a lot of algorithms are tried with existing data set till they achieve satisfactory results. And that is a part of the tuning. And once the data scientist or the developer freezes a model saying it has reached a point where it has learned all the patterns about the data, it moves into what is called as inference. And that's where it gets deployed and then it gets scaled. Again, DevOps comes into picture because a fully trained model could be packaged as a Docker container and deployed in Kubernetes environments or in virtual machines or in any other hosting environment where it needs to be treated like any other workload. So that needs to be safe, that needs to be secure, that needs to be scalable, it needs to be highly available. Basically, get all the attributes of a highly available web scale application because it's going to be used by a lot of consumers coming from mobile devices, edge computing environments, desktops, web apps, and so on. So a fully trained model deployed in an inferencing environment is no different from running a highly scalable web app. So that is the life cycle from the lens of DevOps, developer, and data scientist. Now, cloud has significantly changed the lifecycle management of software. Thanks to platform as a service, which was popularized by early stage PaaS implementations like Heroku, IngenueYard, followed by, of course, Azure's own app service and many of the other PaaS implementations. Software development has significantly changed with PaaS. So in PaaS, what typically happens is you bring your code and then run it on a web scale infrastructure and watch it automatically scale. So you write code that is tested in your desktop environment, which is not very powerful, which is not very scalable, but then eventually you run it in a data center or infrastructure managed by Microsoft or Google or Amazon, and you watch them really scale and automatically shrink. Now, that was the advantage of platform as a service or PaaS. That has been mastered by some of the providers like Microsoft, Google, Amazon, and other vendors that I mentioned. Now, machine learning platform as a service is a logical extension of PaaS to basically support the lifecycle management of ML models. Just like PaaS has revolutionized software development, machine learning PaaS is changing the face of data science, ML experimentation, iterative development, and inferencing. So here, just like PaaS, the data scientist brings a lot of data and then an algorithm that he has tested with a smaller data set, maybe in his data center or even in his desktop. And then this large data set that's been uploaded to cloud, typically in object storage like Azure Blobs, is now going to be applied to the algorithm that he has tested on a smaller data set, and it is going to be trained on a much powerful infrastructure, maybe supported by CPUs, by GPUs, and so on. So that environment where you bring code along with data and you go through the process of training, tuning, deploying, and scaling is typically called as machine learning PaaS. And it extends traditional application platform as a service to machine learning, where it also deals with data, hyperparameter tuning, deep learning, and many other use cases that are very specific to machine learning. And just like a PaaS is accessed from dashboard, which is, for example, an Azure portal, CLI, and an SDK, machine learning PaaS is also exposed via those interfaces. You can log into Azure portal and deal with ML PaaS, Azure ML, or you could provision the entire environment from the CLI, or you could programmatically do it from Python SDK. So Microsoft's own implementation of ML PaaS is called Azure Machine Learning Service. This is fairly new. It was announced at Ignite last year, and then many features got added, and it became generally available recently with many more capabilities like pipelines and MLOps and so on. So the promise of Azure Machine Learning Service is to handle the entire life cycle of machine learning models. And you could programmatically talk to it via the Python SDK. You could use infrastructure as code through the CLI or PowerShell automation. You could interactively deal with it by signing in into the portal. But end of the day, what you're going to achieve with Azure Machine Learning Service is an environment that will dramatically simplify provisioning and configuration of environments, and then deployment and scaling. But the essential training and tuning is still left to data scientists, because it is mostly done as an iterative process. For example, for the given data set and for the given business problem, the data scientist has to try multiple algorithms, and once a couple of them get shortlisted, he has to change few more parameters for those shortlisted models and retrain and iterate till the results are satisfactory. That process is typically iterative and best left to a data scientist. But thanks to an emerging technology called Auto ML, which is supported by Azure Machine Learning Service, even that process is dealt by the platform, which means you bring the data and you use Auto ML on Azure to figure out the entire iterative process, handpicking the best algorithm, parameter tuning, and then evolving the final model. So all of them are delivered by Azure Machine Learning Service. It is exactly like any other PaaS, but deals with a lot of data and the use cases and scenarios that are specific to machine learning. So let's take a closer look at Azure Machine Learning Service. It is essentially a managed service to build, train, and deploy models. So what do you mean by managed? So there are two ways of dealing with cloud. One is you spin up virtual machines, you SSH into the virtual machine, and then you install everything from the ground up and you build your environment. For example, Azure SQL is a managed service, whereas installing SQL Server inside a Windows VM is an unmanaged database. So in unmanaged environment, you are responsible for the uptime, for the security, for scaling, for patching, and maintaining the whole infrastructure, while a managed service will take care of the heavy lifting while letting you focus on your use case, your business, and ultimately the core and the application. So just like Azure SQL takes the pain of installing, configuring, managing, and maintaining the database, Azure ML Service takes the pain away from configuring, provisioning, and setting up the infrastructure. It is a ready-made environment for you to run your TensorFlow, Caffe, PyTorch, or any of the popular open source frameworks with popular IDEs like Jupyter Notebooks or PyCharm and even VS Code. So it gives you the complete environment for you to get started with the infrastructure and popular Python environment framework and tools. And as I mentioned, it exposes Python APIs to perform end-to-end lifecycle management of models. So the key differentiator for Azure ML is empowering data scientists to do end-to-end lifecycle management. In typical provisioning and DevOps environment, the DevOps team will set up everything and then will send a mail or a notification to the data science team saying that here is your cluster, here are the credentials, go ahead, log in and start experimenting. Whereas in Azure ML, whatever is expected to be done by DevOps is also done by data scientists. For example, with just one call, you can create an Azure ML compute infrastructure, which comes preloaded with all the NVIDIA drivers and TensorFlow or Caffe or PyTorch and ready to train your model. And that is just one API call away. So that is a very, very powerful mechanism empowering data scientists to take control of the infrastructure and perform self-service management and self-service operations on infrastructure provisioning, managing, and the entire life cycle. Azure ML can mix and match on-prem with cloud and edge environments, which means there is no hard and fast rule that you have to use Azure compute infrastructure for training the model. Azure ML is more like a platform that will give you a lot of choice. For example, if you have a data center that is capable of training and performing inference, you can still take advantage of Azure ML while pointing Azure ML to your own data center or your own infrastructure that is ready for high scale training and performance training. Similarly, you can train the model in the cloud, bring it to your data center and host it for inference, or train in your data center on-prem and bring it over to Azure ML for inferencing. So there is absolutely no hard and fast rule on using this platform for everything. You can mix and match infrastructure running across on-prem, cloud, and edge. So Azure IoT Edge, which is Microsoft's edge computing infrastructure, is very well integrated with Azure ML. So you can actually create a pipeline that trains in the cloud and automatically deploys the model to the edge environment. Obviously, Azure ML extends the capabilities of Azure, particularly in terms of security, compliance, and virtual network, so that customers can get a very locked down environment as a part of virtual network, and they can decide where they want to run the infrastructure. And the authentication, compliance, policies, all of that is inherited from the proven Azure infrastructure and Azure security model. So you can get the benefits of using Azure Active Directory and some of the existing building blocks when running ML training and deployment. As I mentioned earlier, AutoML is a mechanism to basically let the platform choose the best algorithm for you. So it is a autopilot mode where you bring the data set and you call a couple of APIs, which will figure out the best algorithm to train the model and automatically generates the model that you can use for inferencing. So that is a part of Azure ML. It supports both classic machine learning based on scikit-learn and supervised learning. You can also use it for deep learning with TensorFlow, PyTorch, and basically to generate some convolutional neural networks or some of the RNNs and LSTMs and advanced deep learning models. And it comes with experiment tracking, model management, monitoring, integrated CI/CD pipelines, and MLOps. What it means is all the best practices of agile operations and DevOps are now extended to Azure ML. So you can actually connect your GitHub repo to Azure ML, and every time you commit code, you can actually trigger the entire process to take that code or pick up that notebook and perform model training and automatically generate a model, version it, and push it to an Azure Kubernetes cluster for inferencing. You can automate all of that, and that is actually called as MLOps, which is applying the best practices of DevOps to machine learning management. So that is baked into Azure ML services, and you get to mix and match DevOps with data science. So taking another look at Azure ML, essentially there are three stages. The first one is data prep. So data prep requires a cleansing and exploration, visualization, and basically making sure that you have the right kind of data which is going to deliver an optimal model. Because just like garbage in delivers garbage out, bad data delivers bad ML models. So you got to make sure that your data is in right form before you can move to experimentation and generate your model. And sometimes the data could be so big, so large in terms of the size that you may have to parallelize and run data cleansing and data prep and ETL in a distributed mode. So Microsoft has partnered with Databricks, and Databricks gives you a highly distributed environment for performing Spark or Hadoop-based data transformations. You can take advantage of that to actually prepare data. For example, if you bring a petabyte data set and you want to perform ETL on it, or you want to clean it, perform data imputation, data cleansing, and all of that, you can actually take advantage of Databricks environment. You could also use some of the primitives of Azure, like the data factory and so on, and you can actually use a lot of existing services, including data lake and some of the other data platform components to prepare your data. So that is the first stage. And after that, you move into experimentation, where you try fitting your model to the right algorithm. That can be done via Visual Studio Code, which is an open source editor, or open source IDE, or you could use the most popular Jupyter Hub and Jupyter Notebooks to perform interactive experimentation and coding. And once the model is generated, you can train and test. And after that, you move into deploy phase, where this model is now packaged either as a container or as an edge module and gets pushed to the edge or moves to a Kubernetes cluster or an ACI cluster or an ACI group to essentially expose an endpoint where you can perform inferencing, which is nothing but predictions. So 3 phases: prepare, experiment, and deploy. And you have a lot of choices for each of these stages of the data processing and ML pipeline. So zooming into the compute infrastructure and meant for training and inferencing. So as I mentioned earlier, deep learning models are dependent on high performance computing clusters. That's because they actually deal with complex mathematical computations that happen in parallel, and CPUs are not quite optimal to perform those kind of operations. So you need GPUs, and in fact, multiple machines or a cluster of machines with GPUs configured so that your mathematical computation and compute intensive tasks run in parallel and perform at a much higher speed than on a typical CPU based environment. So to facilitate that, Azure ML gives you the choice of compute targets. As I mentioned earlier, if you already have a fully configured data center powered by NVIDIA or Intel GPUs or FPGAs, you could actually point Azure ML to that, which becomes the compute target. Or you could take advantage of the compute target running on Azure. So you create a cluster that's running Azure VMs powered by NVIDIA K80 or P100 or T4 GPUs, and your training job runs in parallel across the cluster. And as soon as the training job is done, the cluster is automatically toned down. It is shrunk to the minimum size so that you are not really spending a lot on infrastructure. And once the the training process is done on the compute target, then it moves to the hosting, where again you can actually choose the low cost Azure container instances, which is not really meant for production, but for a quick dev test kind of a setup. And for highly scalable production ready deployment, you would take the model and run it on Azure Kubernetes Service or AKS. So this is the entire life cycle. Training happens on the compute target. Inference or the deployment also happens on the compute target. And for each of these environments, you have half a dozen choices. On training, as I mentioned, you can use what is called AML compute, which is Azure ML compute, or you could also use Kubernetes cluster for training. You could also use Databricks based on Spark. You could also run Azure Batch AI, which is again a managed infrastructure for running highly parallelized operations. So take a look at the Azure ML documentation for the complete list on the supported compute targets. And when it comes to inferencing and deployment, the obvious choices are ACI, which is Azure Container Instance, Azure Kubernetes Service, or Azure IoT Edge, which is going to run the container as an IoT module. So at the front and center of Azure ML, there is something called as an ML workspace. So ML workspace is a subset of Azure Resource Group. Now, all of us are familiar with an Azure Resource Group, which acts as a logical boundary for all resources associated with a specific deployment. For example, when you are launching a highly scalable web app, you start by creating a resource group, and then you launch a VM, and then you add a couple of more VMs, and then you configure a load balancer, and then you configure firewall in terms of inbound and outbound rules. And then you actually configure the DNS and you go live. So all the resources that are associated with this deployment stay within the logical boundary of a resource. Now, Azure ML creates a subset of the resource group, which is called as a workspace. And this workspace is highly aligned and specialized to maintain resources that are required for the machine learning job. So an ML workspace is going to live inside a resource group, but it's a hierarchy in terms of the resources, because first you have a resource group and then you have a workspace, and within workspace you have things like image, compute, experiments, models, deployments, services, and so on. Now, these are not going to be visible at the resource group level because they are highly customized and they are very specific to the Azure ML platform as a service. So that's the reason why Azure creates a subset of resource group, which is called as a workspace. So when you actually create a workspace uh, within a resource group, there are multiple other things that actually get provisioned for you. Because Azure ML deals with a lot of containers, both for training and for inferencing, it creates a dedicated container registry under the same resource group. And this is essentially used for pushing and pulling container images. Then there is a storage account. Obviously, machine learning is all about data, and Azure's one of the core pillars is Azure Storage. So the blobs are being used for ingesting the data coming from a variety of sources like Event Hub, Stream Analytics, and so on. Or you could directly upload the data straight into an Azure blob, which is a part of the storage account. So models get written to storage account, data comes in via the storage account, intermediary data is stored on storage account. So it is basically the foundation for all things data. Key vault is basically used to maintain secrets, because we are going to deal with some sensitive data like usernames and passwords, particularly for container registry and even some of the other resources that we may access. So all of them are going to be securely maintained in Key Vault, so that you're not actually using a database or a flat file to store those credentials. So Key Vault is another essential element. When you create a workspace, it automatically gets provisioned for you. And finally, Application Insights, which is going to log all the data and the insights generated by this workload, and you can actually use it to understand the current state of your resource group and the ML workspace, and it gives you a lot of insights into what is currently going on with your deployment, including the ML workspace. So those are the essential elements created when you actually launch or create a workspace. But I'm not showing you what's inside the workspace. I will talk to you more about it when we actually do the demo, but let me show you the Azure portal here. So here, we have two resource groups. So one resource group is called AML demo. Let me show you that. It is a cached resource group where I have a fully trained model just to save time. And if something goes wrong, I can always fall back to this. So this is the workspace. You can actually create a resource, a workspace resource, by going to create resource and typing workspace. So this is going to bring up the machine learning service workspace, but this is not the best practice of creating an Azure ML workspace. You are expected to do it from Python code or the CLI, because no data scientist would ever want to do it interactively from the portal. But assuming they use the SDK or the CLI, you actually end up creating a resource group. And within the resource group, you have all the essential ingredients. For example, you have all the essential ingredients like, as I mentioned, the Azure Container Registry, the Application Insights, the Key Vault, the storage account, and any other container instances or any other compute instances you may launch as a part of this workflow. But the most interesting aspect, which is a subset of a resource group for Azure ML, is called as the machine learning workspace. And here we created a machine learning workspace called salary, which means we are going to train a model related to the salary data. And this is completely an environment by itself. This is not a resource group, it's a subset of the resource group, and it has some assets like experiments. Machine learning is all about experimentation. You will run multiple experiments iteratively, and every experiment gets logged into this. So you can compare and contrast one iteration with the other, and it gives you metrics and other parameters that you can interactively visualize and track. Pipelines, a very powerful feature where you can create a sequence of steps involved in MLOps or evolving the model. Compute is where you can actually define your clusters, both CPU and GPU clusters. So when you actually add compute, you can give it a name and it shows up. So this is how you actually use the compute infrastructure from Azure ML Workspace to train your models. And once the training is done, a model gets generated and it gets registered. It shows up here. A model is nothing but an artifact. It is basically telling you the outcome of one of the training experiments, and it actually shows up here. You can register a model once you are happy with the training process and the testing process and the tuning, and it shows up here. A model is nothing but an outcome of one of the experiments, and it gets registered. Every experiment can actually register a model, and it shows up here. Once the model is frozen, you can turn it into an image. Essentially, this is a Docker container image which wraps the image that you generated in the previous step. And this is going to be stored in the Azure Container Registry created as a part of the resource group. And once the image is generated, it gets turned into a deployment. And a deployment is nothing but a VM or a Kubernetes cluster that is hosting your container model and is hooked up to a load balancer so that you can actually send high traffic requests, and it can be used for inferencing. So all these are the subset of Azure ML Workspace, and they don't really show up when you query the resource group. So even if you launch a compute instance from Azure ML Workspace, you cannot see it at the resource group level because it is still within the black box of Azure ML Workspace. So those are the essential building blocks of Azure ML Workspace when you create it. So now let's actually switch to the demo, and I want to show you a simple machine learning model. Again, the idea is not to overwhelm you with a highly complicated deep neural network. The focus of this webinar is not to overwhelm you with complex machine learning algorithms, but instead show you how to leverage Azure ML. So I want to pick up a very simple machine learning model, and this is based on Stack Overflow salary dataset. So I have extracted some data from Stack Overflow salary dataset. Stack Overflow, I'm sure if you're a developer, you're already familiar with Stack Overflow, and the best thing about them is they actually publish a salary calculator. So if you are applying for Stack Overflow and you want to figure out which band of salary you fit into, you can go to the Stack Overflow salary calculator, give your profile like developer, architect, product manager, designer, DevOps engineer, choose the city where you're going to work from, then rate yourself on a scale of 1 to 5 in terms of your skill set, and then tell how many years of experience you have, and then Stack Overflow will come back to you and tell you the range of the salary. So what I have done is I have taken the salary of a developer with 2 years, rather 2 points of experience, that is skill set, and then multiple years of experience. So that means a fresher who is just getting started with 0 years of experience with 2 points of skills will get about 103K. So that is the starting salary, and I have captured it till 20 years. Now what we're going to do is use this data set to train a model which will predict the salary of a developer working at Stack Overflow based on his number of years of experience. So no brainer, it's a very simple linear regression model. And again, I don't want to pick up a complicated training and algorithm. I want to keep this really simple. So we are going to use this CSV file throughout this demo. So once we understand the data, so basically X represents the years of experience and Y represents the salary. And we're going to train on an extremely limited data set. Again, this is just for the demo, not for, don't try this at home. It's not going to give you good results because we have a very limited, highly constrained data set. So we take this data set and then we perform training. So again, if you're not familiar with Python, scikit-learn, NumPy, pandas, don't worry. I'll just walk you through what I'm actually doing here. So I import a set of libraries and modules like NumPy, which is meant for scientific computing. It gives you array manipulation, vector manipulation, and it is much better than using internal data structures of Python. Then pandas, it's a data processing module meant for dealing with CSV, TSV, JSON, and basically files performing data prep. So then we use joblib, which is basically meant for serializing a model into a joblib or a pickle file. And it is almost like serializing your object and again deserializing it when you're using it in the runtime. And then scikit-learn is a very popular simple yet powerful machine learning toolkit used by Python developers. So from that, I'm actually importing linear regression, which is based on y is equal to mx plus c. Very simple algorithm. And we're also borrowing a helper library for training, for splitting the train and test data. So those are the imports. And then I go ahead and load my sal.csv that I have shown you here. And once I load it into pandas data frame, I split x, which is number of years of experience, y, the salary. And then, as I mentioned earlier, during the discussion on machine learning, I'm going to split this data. 25% goes to test and 75% comes to train. We shuffle the data set. And then what we actually do is we call this method called lm.fit, and lm is pointing to the linear regression algorithm, which is very simple mechanism based on mx plus c. So we basically know m, which is the slope, and then we know the intercept, and we know the x, and we find out y from that. And y in our case is basically the salary of the developer. So we go ahead and call lm.fit, and then it comes back and tells us what is the base salary of the developer, and then what is the increment per year. And using that, we can actually go ahead and calculate or predict what is the expected salary of a developer. So we call lm.predict. So lm.predict is going to take a batch data set, x.test, which has 25% of the original data set. So we feed the number of years of experience to this, and then yPredict will contain the outcome or the results of the prediction. And then we go ahead and compare the original value, which is stored in yTest, with what we have predicted, and we perform what is called as the mean square error to figure out how close we are to the actual prediction. And once we are happy with this, we will go ahead and serialize the fully trained model into a file called salmodel.pickle. So pickle is basically an object serialization format in Python, very popular among ML developers. And then we dump it onto the file system. So the output of this program is generating a pickle file, which is a fully trained program. So let's go ahead and run this. So I'm going to run python train.py. Now this is going to take few seconds, and then it says the base salary for any developer is about 103K. And then for every year of his experience, he's going to get an increment of roughly $1,800. And then the mean square error, which means on a scale, we are plus or minus $3,000 of salary predictions. That means when we actually predict, we are going to be plus or minus $3,000 error rate, which is okay. The lesser the better, but remember, machine learning is not about getting 99% accuracy. If you're actually getting it, you have overfitted the data, and it is not a good sign. So this MSC is pretty good. What it tells is your prediction is either plus or minus $3,000 of the actual salary, which is still okay. So we are happy with this result, and as a part of the training, we have also gone ahead and saved the pickle file. So if you go to model directory, you notice that this pickle file is now generated, and it contains the model. If I actually give it to you, and if you import it and run it on your machine, you'll get exactly the same prediction. So that is a mechanism to port the fully trained model. Now, once the model is trained, the next phase is to basically run it. So we'll run the infer.py. So what exactly is infer.py? Let me show you the code here. So this is called inference. So it's a very simple Flask application where we are exposing an endpoint called /sal, and it accepts a GET request with the number of years of experience, and it prints a JSONified salary. So and before we actually print it, we load the serialized pickle file, we deserialize it, and then we send the GET request to it, and we print out the expected salary as a JSON payload. So pretty straightforward. The key thing here is how we are actually using this model. So now, this is currently running on my local machine. Now, what I can do is I can actually run curl. For example, I'm interested in finding out 10 years experienced guy, right? So this will print out a number, but 10 is already in our data set, so that is not a big deal. But if I actually pass 30 years of experience, it's going to come back and tell that it is about 160K. So this is actually a prediction because our data set didn't contain 30 years of experience. So it is now performing predictions. And now you can actually expose this as a web service, or you can build a nice iOS or Android app and actually say that, hey, here is a Stack Overflow prediction tool. So you can go beyond what the calculator is offering and you can perform prediction. And assuming your application is a big hit, you're going to get a lot of requests and you need to scale, right? So that is the next phase of your ML development and experimentation. So this is how you basically do something in your local machine. But let's say we hit a point where the data set is 10x bigger, 100x bigger, and our local machine is not capable of training this because we have limited resources, we have finite set of resources, and our machine will crash when we try to load this data set. Forget about training. We can't even deal with the data set. That's when you actually move to Azure ML. So now let me switch to Azure ML environment and perform exactly the same thing, but in the cloud. So this was a walkthrough of what we do on our development workstation, but let's switch to Azure ML and then use the Python Jupyter environment to basically perform the training. So some of this is already done because provisioning resources is going to take a long time. So I'm going to skip certain cells of this notebook, but I'll walk you through everything that is involved in training the model based on Azure ML environment. So first we import the libraries. It's not very different from what we have done earlier. So if you look at our train.py, exactly the same set of libraries, nothing different. So we'll first import them, and then we import Azure specific Python modules. So again, all of this is available as a pip install module. So you can actually run pip install Azure ML and you get access to all these libraries. It's better to create a Conda environment. If you're not familiar with it, please refer to Azure ML documentation. It has a very nice step-by-step guide to setting up Azure ML environment on your development workstation. So I've gone through those steps. So now Azure ML is the SDK is installed. I can import all the modules, and one check to make sure that everything is in place is to print the version of Azure ML core. So it says that it is currently 1.0.48, which is the most recent version. So we are now ready to create a workspace. So this is how you basically create a workspace from the code. Earlier I have shown you how you could create it from the portal, but that's going to be non-intuitive for data scientists. Data scientists are more comfortable dealing with Python SDK and Python code. So they want to call one Python as API and from the SDK and provision everything that they need. So what they actually do is they give the name of the workspace. They give the Azure ID, Azure subscription ID. This is based on your Azure subscription configuration, and then give a name of the resource group. This is the standard conventional Azure resource group. And then if that doesn't exist, we are asking the workspace to go ahead and first create the resource group. And we mention the location, Southeast Asia, or any of the supported regions where Azure ML is available. Now, one call to this API will basically result in the creation of the resource group. All the building blocks that I mentioned, like App Insights, creation, the Azure Container Registry, Azure Storage, Azure Key Vault. So you can see that this single call is resulting in the creation of all the resources. And this is going to take 5 to 7 minutes. So I'm not going to do this now. I'm going to skip this. And once you created the workspace, you can persist it to the local configuration file, which becomes available here. So let me switch to Azure. So once you create a workspace and once you call this API called write config, within the current directory where you're running the notebook, there is a new directory created called .azureml. It's not visible with standard ls, but if you do an ls-la, you can actually get to see that. And a file gets written with your configuration. So config.json will contain the resource group and the workspace definition, so that later on you can simply load it from the config. So now I'm actually loading it from my existing config. So when you actually call ws get details, it comes back with everything that is available within the workspace. For example, it tells you the name of the workspace, the location, the friendly name, and also all the resources that are created, like the storage account, everything. So you can retrieve the configuration from get details, but for the first time when you're running it, you got to create it. So I'm skipping it because my workspace is already in place. So once the workspace is loaded, from that we go ahead and create an experiment. So an experiment is a mechanism where you can track metrics. As I mentioned, machine learning is an iterative process. Before I arrive at a fully developed and fully trained model, I might have to experiment a few dozen times. And how do I know that my experiments are performing better or getting better with every iteration? I need to log some metrics. For example, there is a metric called loss. That is basically how close you are with the test data set, and the learning rate, right? The number of epochs that I'm using, the batch size of my data set. So there are certain metrics that I want to fine tune and modify for every iteration of the experiment, and I'm going to log them to Azure so that it is recorded and I can compare and contrast and I can visualize, I can generate nice charts, but all of that is available as a part of experiment. So I go ahead and create an experiment, and then I'm going to start logging the metrics. So Azure ML gives you a nice API to perform some logging. Instead of printing it to the standard out, you could actually divert them to Azure logs, which are going to become available visually on the portal, and you could also retrieve them programmatically at a later point of time. So now I first record the experiment start time, and then I follow the same scikit-learn process. I'm going to use pandas to load my CSV file. I'm going to split the data set and then train the model and save the model to a directory called outputs. This is very, very important to understand because there is a significance attached to this. I'll come back to it. Let me complete this experiment. So now I'm going to test the model. Testing seems to be working fine. So when I actually send 21 years of experience, it is coming back with a prediction of 141K, which is not bad. And I'll also load or rather log the metrics like intercept and slope. Now for scikit-learn, this doesn't mean anything, but when you're actually using TensorFlow or PyTorch, logging these metrics will become super useful and helpful when you're iterating over the training. But for the sake of showing you the metrics, I'm actually logging the intercept and slope. Now I'll go ahead and end the experiment, my first iteration. But in a traditional deep learning environment, this is going to be in a loop, and we will run it multiple times with different hyperparameters and different tuning parameters. So now let's come back and look at our workspace. So we have a workspace called webinar. That is the webinar workspace. Let me open it here. So we'll go to resource groups, and our current workspace is provisioned inside this resource group called webinar, and within that there is this salary workspace, and then we have experiments as an asset. So when I click on experiments, you'll notice that whatever we have logged from the Python Jupyter notebook becomes available here. So sal experiment, and this is what we mentioned when we created the experiment, and it is actually visible here. So when we launched our experiment, we called it as sal exp. So that's what is now available to us here. So this is the intercept, this is the max slope, 1 completed, 0 running. You can actually click on all the runs, that is multiple iterations within the experiment, and you get a nice view of all your parameters. And again, for scikit-learn, it doesn't make much difference because we don't use hyperparameter tuning, or there are no complex parameters involved. But in deep learning experiments, this is going to be very, very useful. So that is experimentation. And remember, I'm still running it from my local machine, right? So we are not using Azure ML Compute. So at this point, we are still using our local workstation to perform the training. But in production use cases, for example, if I'm using TensorFlow or PyTorch or Caffe or CNTK, my machine may not be powerful. So at this point, what happens is just before I start the training, I create an Azure ML Compute instance or instances, because I'm going to create a cluster. And to that cluster, I pass my training program, and it is going to run in a distributed mode. And at some point, when the model gets converged, it is going to give me back the model. And that model is going to be picked up by Azure ML environment, and it gets turned into a service and eventually a deployment and so on. Actually, first deployment and then a service. So in our case, no, we are actually using my local machine, but just before you start the training, it is possible for you to delegate and offload the training job to Azure ML Compute. Now, remember, I mentioned that there is this important directory called outputs, and we are currently emitting the pickle file into that. So what this actually means is outputs is a designated folder for Azure ML, and anything that you put here will automatically get uploaded to Azure storage, and it becomes available as a model. So once the job is finished, you can actually go to activities, and here you will notice that the entire experiment is now logged, and you can see the okay, so it's actually visible here. So you'll notice that whatever we run on our local machine is going to be uploaded into this, and eventually the outputs directory, whatever we put inside that, will also make it to the cloud. And to do that, I need to basically register the model. So we have tested the model, everything looks good. Now what we'll actually do is we will register the model. So when you run this, when you call this API called model.register, you are telling Azure ML that please pick up the serialized file that is currently residing in the outputs folder, call it sal model, give it a key which is a tag, and call it salary prediction, and upload it to this workspace configured as WS. Now, when we come to models and when we refresh, we'll actually notice that our salary model called sal_model is now registered with Azure ML. So this is going to be used by the next step, where we package it into a Docker container and then eventually deploy it on Azure Container Instance. So let me refresh. Sometimes the Azure portal, particularly the workspace access, takes a little longer. So let me click on models, and we should see, there we go. So the SAL model is now registered. It is available for us for inferencing, and it contains exactly the same metadata that we have passed, like the key, the description, and so on. Now, once the model is generated, we need to deploy it into one of the compute targets. As I mentioned, for the model deployment, you could actually target Azure Container Instance, which is a serverless container infrastructure on Azure. You could also deploy it on AKS, which is Azure Kubernetes Service, meant for production use cases, highly scalable inferencing environment. Or you could also push it to IoT Edge environment, which will be delegated via the IoT Hub, but that's a very different use case. So now what we'll actually do is we will ask Azure ML Workspace, I mean the SDK, to take this model that we have registered called salary model, and then deploy it into ACI. So ACI is Azure Container Instance, but what will an Azure Container Instance do with a pickle file, right? A pickle file is just a serialized blob. Now, if I just give you a pickle file, you can't make anything out of it, because I'm not telling you what to expect as an input, what to expect as an output, and how do you use that. It is almost like giving you a DLL and you don't know what to do with it. At least for DLL, you can introspect and figure out what it contains. But if I just give you a serialized .NET object, you don't know what to do with it. Similarly, a pickle file is pretty useless if you don't know how to invoke the model and what to pass and what to expect. So we need to tell Azure Container Instance that along with the model, the pickle file, we need to have a couple of files. So what we'll do is, on the fly, we create something called score.py. It actually becomes more easy when we open it in editor. So what we'll do is, along with the pickle file, we pass a scoring file, and this is the scaffolded format, that is expected by Azure ML, and it's not really rigid. Basically, there is an init method where we define the global object called model, and we deserialize the pickle file and we load it into model, and then we have another method called run, and this accepts raw data, which is coming from the curl or any of the REST clients. And this raw data gets converted into a JSON string, and we convert that into a NumPy array, and we pass that NumPy array to our model, and we send the output back as the HTTP response. So this code needs to be front-ending the pickle file. Without this code, pickle file is pretty useless. So now we're actually telling that apart from the pickle file, push this code into the container image, which is going to be deployed on ACI. And again, this file is great. It tells how to deal with the pickle file, but how about the dependencies? How does the Docker container image builder know that it has to install sklearn, it has to install NumPy, it has to install pandas, whatever you're actually using? So what we'll do is we'll also create another file that is called conda.yaml. So we can give any arbitrary name, which is salenv.yaml. And what this is going to contain is the dependencies defined in a YAML format. So now we're actually creating this YAML file that says, please use Python environment 3.62, Azure ML defaults, install scikit-learn, and pull all this from Conda Forge. So this is actually an input to Conda. Now, the way Azure ML works is it basically parses the YAML file. It figures out which version of Python it needs to install or create a virtual environment. And then it will pick up the modules mentioned under pip. So we need Azure ML defaults. Then we need scikit-learn because we are actually using scikit-learn in our scoring.py. And it pulls all of them and does a conda install or a pip install and creates the environment. After that, it pushes this core.py, and finally, it turns into an image. So now we have actually created a Docker image with 3 files. One is the pickle file, which is a serialized model. Then we are creating a YAML file that tells what are the dependencies and pip modules to expect. Then we are actually front-ending the pickle file with a scoring program, which is core.py, and we are pushing all of that into the Docker image. Now that Docker image alone is pretty useless because you need to run the Docker container and expose it to the outside world. That's where we take help of ACI. So we take the Docker image and then we turn this into a service. And this is going to take a good 10 minutes. So I'm going to skip this step while we are waiting for it. So finally, what happens is the entire image now gets turned into a deployment. And this deployment is available as a URL. So this URL is now available to the public. And because we are using ACI in a dev test environment, we are not securing it. But for production, you need to have SSL enabled and have a TLS configured endpoint. But we'll grab this endpoint and we can actually make a curl request. So let's come back to our notebook. And now we will hit the curl endpoint. So we are sending this input data for 45 years, and we should actually see a number here. So let's wait. I'm not sure if this is still up and running. This is my staging environment where I have gone ahead and deployed the model and turned it into a service. Not sure if this is still alive, but if everything works, this is not going to work because it's waiting for the remaining cells to complete. So what we'll do is we'll switch to the command line and run this thing. There we go. So now we're actually hitting the endpoint running on Azure. And as soon as this is executed, you see a number, and this number indicates the salary for a developer with 45 years of experience. So now we have gone from local machine to the cloud for inferencing. And finally, we can invoke WS delete, which is getting rid of the entire workspace. I'm not going to do it now, but once you are done, you can actually delete it because your model is now moved to inference and you don't need this workspace anymore. So that's the workflow involved all the way from training to inferencing, and that is Azure ML for you. So to summarize what we have built, so an ML model based on scikit-learn, we trained the model locally, then we took help of Azure ML experimentation to log the metrics. We registered the fully trained model with Azure ML as a container image, and then we launched the container image on ACI for serving. So to quickly summarize, we are at the top of the hour, we are running out of time, but just to summarize, Azure ML service is a PaaS, just like you run app service for API and web hosting, you run your ML training jobs on Azure ML service. It empowers developers and data scientists to programmatically manage the lifecycle of ML models. Workspace is the logical boundary where all the assets related to your machine learning are maintained. There is a wide range of compute choices from your local data center to AML compute to AKS clusters to FPGA based VMs. You can use a variety of compute environments. Comprehensive model management, versioning, and experimentation. For every iteration, you can log all the assets to Azure ML Workspace and track them. And finally, you can publish your model as a web service running in AKS or ACI, or push it all the way to an edge module via IoT Hub. So that's the end of this session. Again, there is a special offer for the attendees of this webinar. You can get 10% discount on a variety of courses. Get in touch with Martha if you need more details. The email ID is mentioned right here. So let me see if there are questions. There are quite a few. I'll try to answer a couple of them. And looks like there's a standard question on whether the recording is going to be made available. Absolutely. This is going to be available on, I think, YouTube. You'll receive an email with the link.
I actually sent everybody out the link, Yanni.
Okay, fantastic. Okay, so there are, okay, do you create a VM first and then launch Jupyter? Not exactly. The Jupyter environment is running right off my machine, but there is something called Azure ML notebooks. You can actually use that to launch a notebook. For example, when you switch to this, when you go to the home page of your workspace, the landing page within the portal, you'll see there is something called Azure ML notebook. So you can, it's currently in preview. You can get started with the notebooks and you can launch them right from the Azure environment. But in my demo, I've been using it from my local machine. I also want you to take a look at one of my previous articles. So on NewsStack, where I typically write, I have published a detailed article on using Azure ML service. Unfortunately, I don't have that link. My apologies. I should have thought about it. But if you can search for Janakiram, the NewsStack Azure ML, you'll actually hit a bunch of links that I have already published, and you can go through them. Even the code is on GitHub, and the articles have pointed to the GitHub link for the data set, the training code, and everything. So you can actually try it at your own pace. So there are not many questions. Now, most of the questions are about my association with Wintellect. I think a lot of you are interested in understanding what I teach and when is my course available. Well, I don't teach yet, but very soon I'm going to get started, hopefully on Azure ML. So thanks for your interest, and I will try to bring something to you. And I hope you found this session useful. So if you have questions, there is an email ID mentioned here. Please drop a note to them. And if it is a technical question, I will respond to you. Thanks once again. I hope you found this useful, and I look forward to seeing you in some of the future webinars hosted by Wintellect. Thank you.